Hi guys, it's Madeline again. I hope you are having a wonderful meeting. I hope you all had a wonderful day. Today we're back in the Science Fair lesson video series with week 3, lesson 3 from the Science Fair workbook. Last week we went over the two main branches in the Science Fair process where either you pick a experimental design project where you do an experiment and you create a hypothesis, or the experimental design engineering project, engineering goal and criteria and constraints, whether you go that route. So last week we basically looked at both of those and compared, and this week what we're going to do is we're going to do a quick refresh on them, and then we're going to get into the actual process of writing your hypothesis and writing your engineering goal and your constraints and your criteria. So without further ado, let's get right into it with example time, and we're going to just go over an example, and then you can use these examples to kind of better apply the branch that you chose last week for your project. So hopefully, with your idea of whichever branch you think best applies to your particular project idea, pay attention and kind of take notes so that this example, we can make it apply to your project and so that you have like a base template that we're going to work with. So let's start. In this step of the science fair process, the main focus is turning the aforementioned science fair topic, not the highlighter, we're going to turn the aforementioned science fair topic, so basically the real world problem question that we wrote down 2 meetings ago. We picked whether we want it to be an engineering goal project or if we want it to be an experimental hypothesis project, and we're going to turn that topic, respectively, into an appropriate problem question. We're going to establish variables and finally understand and create a hypothesis if we are doing an experimental project. And then for an engineering project on this side, we're going to turn our topic into a problem question. We're going to create criteria and constraints, and then we're going to ultimately create our engineering goal. So we're going to look at our experimental design example. So a project is being done to test the impact of paper airplane design on how far it will travel. So I know that last meeting, on top of going over those 2 branches, we also went over main big key science fair vocabulary terms. We talked about variables, we talked about hypotheses, we talked about criteria and constraints. So based on this experimental design example, let's practice a little bit more just to refresh ourselves on what we're going to identify as our independent variable and our dependent variable, okay? So one more time, the project is being done to test the impact of paper airplane design on how far it will travel. So I think we can clearly identify something that we're going to be changing. We're going to test the impact of different paper airplane designs, and then what we're going to measure is how far that plane will travel. So it sounds like we have 2 types of variables. What type of variable is this? Last week we called this the independent. And then this one, we're going to measure it. We're going to measure how far it travels. So this is the dependent variable. Okay, so the student is very interested in aerodynamics and airplanes, but saw the real-world issue of the major lack of fuel efficiency in some of the planes. Thus, by identifying characteristics that will improve the aerodynamics of a plane, the student plans to improve airplane design for better fuel efficiency. So I hope you can see how, for the same problem question, we can split it up into basically 2 different potential projects. We can use regular experimental testing with an independent variable and a dependent variable where we do an experiment on the impact of different paper airplane designs on how far it will travel. But then we can also identify characteristics that improve the aerodynamics of the plane and then design that plane for better fuel efficiency. So what does this sound like? Identifying characteristics that improve aerodynamics. To me, if we're going back to our vocabulary, that sounds like some criteria. So those are our goals for our design. So you can take the same problem question and break it down and go both branches. It just really truly depends on what you believe is the best fit to create your solution. So for both of those lines of reasoning, lines of logic and thought, we still have to create a problem question. So back to the example board that I have here. At the top left, we have our big problem question. That is basically where in a big chunky few sentences, you're going to summarize what the real world problem is that you've picked to solve, what your question is as it pertains to this research. So what question kind of sparked your experimental design, or what question sparked your actual like hypothesis and experiment plan versus like a design project. So you can compare, both basically work. You just have to create a problem question that could apply to either side of this. So that's why with engineering projects and with experimental projects, they're a little bit different, but the problem in question applies to both. So I designed a little bit of a problem question template for you where we're going to create our problem question and we're going to just do it together. And this is super easy. This is something you can very easily follow. So what I recommend, go to your computers and pull up a Google Doc, the same one that we've been working in, and we're going to go over this problem question template, and that way you can go ahead and practice writing your problem question for your actual project. We'll be able to go back and refine these, but this is just to give you the most basic idea. At this point, you can pause the video, and members who have done science fair previously, you can go over kind of what the problem in question, why that's important for your presentation. Basically, this problem in question is going to be what is sort of driving this experiment. You are doing this experiment, or you are creating this engineering design product in order to solve this problem in question. And this is the kind of, you're introducing a line of reasoning, kind of almost a storyline, the introduction to your story for what people are going to understand your project as. People are going to hear your problem in question, and then they're going to hear your solution or what you found from your experiment later on once you've gotten through your conclusions and gone through your data. So you're building like your whole project arc here. You're building your backstory. This is the very first most important step. So the problem question template. First, you're going to research one statistic, and then you're going to combine that statistic with a one-sentence description of what real-world problem this project is addressing. So if you don't know what a statistic is, that's a percentage or some kind of like numerical data. You could say like 1 in 5 people will develop lung cancer or something like that. That's just an example. I don't know if that's true. Or you could say like 50% of students experience burnout at some point in their academic career. That's a statistic. So that's very important. Research plenty of statistics that are relevant to your project topic and to your research topic. So you're going to combine your one statistic with a one-sentence description of a real-world problem that your project is addressing. We already basically have that. You can tweak it to where it makes sense. You can say, you can basically provide a statistic about this real-world problem. So, for example, you could say 15% of people suffer from lung cancer, and lung cancer has this of an effect. You can describe what lung cancer does. You can say lung cancer basically prevents people from being able to breathe. It can cause abnormal growths to appear, and it is a chronic illness. It can ultimately be fatal. There are stages to this disease. Kind of summarize the majority of your issue, like the majority of your problem, your issue, into one sentence. So what I would say for lung cancer, 50% of adults over the age of 65 are at risk for lung cancer, which is an extremely fatal chronic disease that affects millions of adults worldwide. That is a big problem. And so you're stating that problem and you're adding a statistic. It gives you some vitality. Then after you do that, after that sentence, this is how you're going to phrase your problem question. Could, and then blank, fill in the blank, state what you plan to test or design. So for example, could a new treatment or medication for lung cancer ultimately, and then you're going to fill in the blank, and you're going to fill in the blank with an explanation of how this project or test will solve the problem in the real world. This is a big picture application. So for lung cancer, you could say, could a new lung cancer medication or treatment ultimately alleviate the current lack of treatments that are out there for people with lung cancer and prevent early deaths from lung cancer patients? You could also make it more specific. You could say, could this particular treatment ultimately reduce lung cancer deaths from predisposure to specific chemicals in older adults? See how that gets a lot more specific? This is a big picture application. So after you say that, you can ultimately go kind of more into detail about how your treatment or your project or your test could identify some kind of a bigger overarching information that can save people, that can innovate a field, that can revolutionize information that's currently out there, that provides something new for the community of science. This is your point where you're going to kind of tell the audience, tell whoever's listening, tell the judges that this problem that you are trying to solve, it's a big deal, and your project directly has kind of like a clear solution for that problem. You're directly addressing your problem. And that's what the problem question part directly is having to do with. It's just addressing the fact that you are creating a solution for this problem and you're telling the audience what the problem is. So this template applies to both engineering design and experimental design projects. So we will go ahead and use this same paper airplane example to fill out the template. So for the paper airplane example, according to the International Air Transport Association, improving aircraft aerodynamics could reduce fuel consumption by up to 10%. So we've hit our statistic requirement, and we also generally stated our problem in a sentence. So airplanes lose efficiency when drag and poor aerodynamics design increase fuel use, which significantly raises carbon emissions and operating expenses. So we've got our statistic up here. We've got our problem in a sentence in that next sentence, and then we're going to say, this is our solution right here. Could changing the design of paper airplanes reveal which shapes or folds improve aerodynamic performance, ultimately helping engineers create more fuel-efficient airplane designs in the real world? So we have very clearly, we're asking our question if our particular solution to our problem, changing the design of paper airplanes, could it reveal which shapes or folds improve aerodynamic performance? That's our question. That's how our experiment or test or design applies to the aforementioned problem up here. And then we're connecting it to the real world. Ultimately, this could help engineers create more fuel-efficient airplane designs in the real world. And that directly connects how we're going to solve our problem and how our particular solution addresses that problem. So now I'm going to go back up, pause the video, and take a second, take as much time as you need to go through this problem question template, have one sentence of a statistic, have a one-sentence description of what real-world problem this project is addressing, and then make your question that's specific to your project, and then you're going to determine, you're going to explain how this problem solves, or how this solution is solving your real-world problem. So follow this template, create this exact design. Basically, I would really highly encourage you to follow this template, and then you will be set up with your problem question. Okay, once you have completed that, we're going to move on to variables key concepts review. So this is for people who are doing an experimental project, not an engineering project, but it's very important for anybody doing either project to listen, because when you're doing your research, you're going to be reading a lot of different scientific journals, scientific articles, and research papers, and you want to understand these key concepts, the independent variable, the dependent variable, what they're controlling, what they're changing, and what the result is. Understanding these key big ideas really helps you grasp in real papers, it'll help you grasp what they're talking about, what they're changing, and then you can ask yourself important questions about why they're changing it and why they got their result. So this is our variables review. To identify variables involved in a project, we must first classify them. To find the independent variable, ask yourself, what is different or being intentionally changed to produce some effect? For a proper scientific experiment, please note that there can only be one independent variable, only one, to ensure that a clear cause and effect relationship can be identified. In the paper airplane experiment, the independent variable is the type of airplane design being used, because that's the thing that we're changing. This is clear because the student is changing the design and trying to measure an effect. Now let's look at your experiment and determine what it is that you are testing and changing. That is your independent variable. So in your Google Doc, I would like for you to pause the video, everybody together, and take a moment, talk about what your particular independent variable is. If you're unsure, ask questions, please let me know, and then that way you can have it written down. So write down in your Google Doc what your independent variable is. So that way we have it, that way we can refer back to it in the future and use it to design your experiment. Okay, now that we all have our independent variable, we're going to look at the dependent variable. To identify the dependent variable in a project, think about what it is that you are measuring or observing as a result of the change that you made. Using your independent variable, ask yourself, what will happen as a result? That's the big question. What will happen as a result of changing the independent variable? That's your dependent variable. The dependent variable represents the effect or outcome of the experiment. In the paper airplane project, the dependent variable is the distance that each airplane travels, since this is what the student measures to see how well each design performs. This measurement helps determine how the changes in the airplane design truly affect flight performance. So the hint, these are the numbers that you're going to compare and analyze. If you're ever analyzing data, if you're comparing things, you're comparing the different results, the different effects, or the different values, I guess, of the dependent variable. So the results that we're analyzing, it's always going to be the dependent variable. All right. And also, quick refresher, super quick, do we remember what axes the independent or x variable is and the dependent variable or y variable is? Go over it for a second in the meeting. Okay, I'm going to go ahead and tell you. This is the x variable. This is the y variable. We have to remember that. The x-axis always holds the independent variable. It's horizontal. And the y variable, it's always vertical. It's always the dependent variable or your results. Very common independent variable is time, because time is constantly changing. And for example, in a situation where you're monitoring plants over time or the number of bacteria over time, time is going to be your variable in seeing how things grow usually. So that is just a rule of thumb. But back to creating your dependent variable. Now look at your own experiment and identify and write down in your Google Doc what it is that you are testing or measuring. And that is going to be your dependent variable for the experiment. Pause, take a moment to review, and then we'll come back all together once we have our dependent variables. Next, and our last big variable that we're going to have to come together and figure out today, that's going to be the controlled variables in a project. Focus on what must stay the same throughout the experiment to make sure your results are fair and accurate. Controlled variables are the factors that could affect your outcome if they were not kept consistent. Proper control variables make sure that the independent variable is the only variable being tested. In the paper airplane project, the controlled variables include the type of paper used, the throwing force, external forces like wind, location of testing. These factors remain constant so that the only difference influencing the results is the airplane design itself, which, if we remember, that was our independent variable, or IV for short. So, like we said previously, all of our controlled variables are going to be things that other factors or other things that could otherwise impact the way that our results come out. So, like we said, wind, the location, throwing force. Also, if there's any differences between testing groups. For example, if one testing group was in a windy area, but the other two were not, that is still very much a variable that needs to be controlled. We can't present data where the conditions were different and there could be outside things that are messing up or skewing our data and creating anomalies, which are random points in your data that don't make sense. And the more anomalies we have that are caused by these different uncontrolled variables, the less credible our data is, the less sure we can be that we have actually established this cause and effect relationship. So in order to make our science more and more accurate, more professional, more precise, we want to therefore minimize as many of these external factors as possible by controlling these variables. So now look in your own experiment and decide what needs to stay the same, what you need to control, and those are your controlled variables. Keep in mind there should be many of these. For example, if you're doing anything where you are doing anything medically related, if you are doing anything plant related where you are mixing or touching parts of your experiment, then you need to be sanitizing everything. That is the number one controlled variables. Everything needs to be sanitized. Everything needs to be kept in the same condition. We can't leave like certain testing groups outside, certain testing groups in the fridge. Everything needs to be kept in a similar area. They need to be undisturbed. We can't have some person like come over and mess up one of your samples. Like those are all things that we need to think about and write down as our controlled variables. Okay, so once you do that, go ahead, write that in your Google Doc, take a moment, pause, and then we will revisit when we get back. Okay, we're going to go over now the same sort of deal for the engineering design projects because we just did the experiment projects. So for the engineering design, a project is being done to design and test a low-cost water filtration system that can make dirty or unsafe water drinkable in areas with limited access to clean water. The student noticed the real-world issue of contaminated drinking water in developing regions and during natural disasters where clean water can be difficult to access. By designing a portable, affordable, and effective filtration system, the student plans to improve access to safe drinking water and reduce the risk of waterborne diseases. So to find criteria, remember we talked about criteria previously, identify the requirements that your design must meet in order to be considered successful. So we listed a couple up here. So these describe features, functions, or goals that your solution should accomplish. In the water filtration project, the criteria include producing clean and safe water, ensuring portability of your device, maintaining a low cost. These goals show what the design is expected to achieve in order to be successful, and that's how you're going to measure what success is and what a prototype is that isn't successful. You have to be able to differentiate those things. So now if you are doing an engineering project, look at your engineering project and determine what your design must be able to do or accomplish in order for you to consider it a success or a solution to your problem. Those are going to be your criteria. So again, go into your Google Doc and write down for your particular project what your criteria are going to be. Next, we're going to look at constraints. Constraints identify limits or restrictions placed on your design. These can include materials, time, size, costs, environmental conditions, or safety concerns. Safety concerns are huge in science fair. Constraints keep your project realistic and help you design within specific boundaries. In the water filtration project, the constraints include using inexpensive and easily available materials. That was one. Keeping the device small enough to carry, so it's portable. That's 2. And ensuring it can be built safely and within a short time frame. That's 3. So these factors limit how the project can be built. They kind of give us some boundaries. But they can also encourage creativity and problem solving so that you can actually accomplish your goals while remaining within these constraints. So one thing I do want to bring up is safety concerns. With our engineering projects, our constraints oftentimes are going to be that we can't necessarily test certain things. There are many things that we can build models that are in scale to test, but the example I want to give you is if we are somehow creating a medication for a chronic illness like diabetes, then we cannot, for safety concerns, we cannot test these medications at first on humans. So in our science fair project, we're going to have to be able to find a way to evaluate our prototype without involving human testing, without involving putting animals or test animals or people at risk at all. For safety concerns with our constraints, that could also mean something like in your design, if you are creating a machine. I've brought up this idea about optimizing a toaster somehow. We have to make sure that the toaster does not exceed an internal temperature of such and such degrees, because otherwise the toaster could explode, and that could be a huge safety concern. In the past, I've had to do projects where a student was using a hair dryer in order to simulate car exhaust. And in that project, we had to very clearly constrain the prototype itself, because the hair dryer produces hot air. And so that was a big safety concern since we were using metal tubing. So we actually had to make sure that the cool button was constantly being pressed and we were using cool air. And so that's kind of another thing that you can incorporate into your constraints. Some logistical and realistic constraints that have to do with the construction and the operation of whatever it is, whatever product you design and engineer. So now look at your own engineering project and decide what boundaries you must work within. Those are your constraints. So go ahead and go back into the Google Doc for those engineering projects and go ahead and write down all of these constraints and confer with each other. That's basically your last step for constraints, criteria, and all of your variables. So congratulations, guys. All right, coming back, this is our last thing for today, I believe. We're going to look at our hypothesis template. I'm going to have you guys copy this down into your Google Doc. Our hypothesis template, we went over it a little bit in a previous video. If, and then you're going to state your independent variable is manipulated in a certain way, then you're going to say what you think your measured result will be with the dependent variable. That's exactly how we're going to structure our hypothesis and put it in that if-then format. So this format helps you make a clear cause and effect statement. It's a statement, it's not a question. The if part describes the change you are going to make in your experiment or your independent variable, just so that we remember. I'm going to write IV. And then the then part predicts what you expect to happen as a result. That's your DV, dependent variable. In other words, the hypothesis connects what you are testing to what you are measuring. Once your variables are finalized, you'll be ready to use this template to write a strong and testable hypothesis for your project. So go ahead, copy this template down. Your homework is going to be to draft up a hypothesis using that template that we can look back upon and finalize later. You will get feedback on your hypothesis and we will help you write your hypothesis. But today we want to make sure that you are mainly getting all of those variables written down, that you're getting your criteria and constraints written down, and that you're starting to write your hypothesis. It doesn't have to be finalized. And that way we will have something, the student leaders, Ms. Hepler and I, will have something to give you feedback on, and we'll know good ways to guide you and sort of nudge you in the right direction for your experiment and research phase. So I will go back up to the hypothesis in 1 second after we finish this chapter, but that's kind of the game plan. As you move on to the next step, which is research, use your research to guide your prediction. This is the thing. You may not exactly know what it is that you think will happen. I'm just introducing this hypothesis template to you so that you kind of ahead know what it is that you're going to have to do. So that way this can guide you in your research when you are figuring out what you believe the outcome of your potential experiment might be. So Make sure your prediction for the hypothesis projects, the experiment projects, make sure your prediction is supported by scientific reasoning and realistic to test safely. Again, like I said, there are a lot of stipulations sometimes. For example, instead of saying for your hypothesis, plants grow better with music, using the if-then template, you could say, if I play classical music for plants, we have the if, our independent variable, playing classical music versus not playing classical music, then they will grow taller in centimeters compared to the plants with no music exposure. So we've got our then, we have our dependent variable compared to plants with no music exposure. So that's an important sort of step to mention. Does anybody remember what we call that? You're right, those are our controlled variables. Let me label this one time so that we can kind of see it. After you guys come together next week and you guys have written your own hypothesis, it may not necessarily be next week, it may be sometime down the road, but once you've written your hypothesis, we are going to break it down like this and diagram it with you so you can identify your independent variable, your dependent variable, and a little bit of your control or like background explanation, putting your testing group into the context of the experiment. So remember, your hypothesis does not need to be correct to be valuable. I cannot restate this enough. I have had students go back and change their initial hypothesis just to say that their hypothesis was correct. Legitimately, that does not mean anything. Actually, sometimes being wrong about your hypothesis can be even more valuable because you have then the opportunity to explain to the judges why it is that you were wrong. So even disproving a hypothesis leads to new discoveries. Later, whether your results confirm or disprove your prediction, your hypothesis serves as your scientific compass that guides you through your research and helps you design an experiment to test your initial idea. If writing your hypothesis is still confusing, skip this step for now and complete the research and project planning chapters. Once you've clearly defined your experimental groups, interventions, and testing methods, forming a hypothesis will become much easier because there will be multiple independent variable options or testing groups to choose from.